Welcome, everyone. Thank you very much for joining today's seminar. Today's presentation is on rockfall mitigation tactics and techniques. Our presenter is Dr. Martin Woodard. Dr. Martin is a chief rockfall engineer from GeoStabilization International. Dr. Martin Woodard earned a BA in geology from State University of New York at Potsdam College, a master's degree in environmental and engineering geoscience from Radford University, Virginia, and a Ph.D. in engineering geology from Kent State University in Ohio. He has authored the Rockfall Hazard Rating Matrix and Rockfall Slope Design Manual for the Ohio Department of Transportation, and he has worked throughout the United States and South and Central America. Thank you very much, Dr. Woodard, for your talk today. I turn it over to you.
Hey, thanks. Thanks. So all these webinars are interesting. One of the things that I heard from you, Mohammed, was that I was in school way too long. And the big joke is I actually went to college longer than I did public school systems, which is actually true. So welcome, everybody. I wish we were live. I wish we were in person talking about this and be able to interact with each other, but we have webinars right now. The first thing I'd like to talk about is the length of the webinar. This is probably about a 40-45 minute presentation. Please submit questions. During the presentation if you want. They'll be reading, and if there's anything really interesting, Andrew, just go ahead and click in and we can go ahead and answer those, or we'll just wait until the very end, whichever way we want to do that. Let's see here, safety moments. So when we're looking at safety moments, we're looking at things that we really have to concern ourselves with. And one of the things that has come to my attention now, especially that I've got a 17-year-old that is starting to drive at night, is this time of year, we do have a lot of wildlife that are going out and are onto the roads. So to take some caution and be careful of that when you're out there driving. And as we're taking a safety moment, everybody, please be careful and pay attention to all the COVID-19 stuff that's going on, and let's see if we can get rid of that. Let's see here, the agenda for today. We're going to talk briefly about rock slopes. We're going to look at identification and characterization of the hazards that are related to rock slopes and to rockfall. It's a specialty area within geotechnical engineering and geology. We're going to be looking especially at some of the mitigation design options. So if you have rock falls, what are the different things that you can do to mitigate? And while you're looking at those, how do you choose which one to do? And one of the things we could look at is the issue of maintenance or budget. And we'll talk about that as we get to those particular parts. And so we'll talk also about some other considerations to take into some mitigation hazards. So when you're looking at rock falls, I always like to start with something that gets everybody's attention. And hopefully everybody can hear this. This is down in Alabama, so I'll let you listen to it. Hopefully it's going to go. 2, there we go. 1, fire in the hole!
Holy shit! Don't get no better.
If anybody's worked on a construction site, you know when anything exciting happens, you have to make that exclamation. So if you go back to the very beginning of this slide, take a look at what's going on. We have this block that's out here that is being undercut. And so we just had a slab recently that had fallen off here because it had been undercut by less durable layers. So in this case, we are dealing with rock falls. Rock is going to be falling down. We have all this debris down below from the recent failure and how we mitigated it. In this particular case, is we had to get rid of it in a really fun way. Even the state DOT had fun while we were doing this particular type of job. So that's just get everybody started with everything. Rock slopes do present hazards. Here is in a quarry. And I just want to note that here we do have failures along a high wall. And if you can look at all this material that fell down, we can actually see the size. and the scale of the hazards that get associated with the rocks. Rocks just don't always stay where they are. They will fail, and we can kind of predict when they are going to fail. So this is a rather large type of failure, but even smaller failures can be hazardous. So the rock that hit this is only about maybe 2, maybe 3 feet in diameter, and it came down and it impacted this excavator. First off, you can try to imagine what happened to that operator, but if that thing wasn't there and he was just standing there, what the kind of hazards that can be presented. So even smaller blocks can be quite dangerous and quite hazardous. So you do have these hazards that are associated. You can have high walls or rock slopes that fail in large amounts of material. So here you have a piece of equipment that's been buried. You have a toppling mechanism on this high wall. And you can see a lot of the high walls have been pretty good, but this one section came out. And when they fall, they have an awful lot of force. So this introduces the field of rock slope engineering. And so as I said, it's a specialty field of engineering or geology, and it deals with the stability and the safety of rock excavations, mainly dealing with civil and mining activities. And there's been other places that we've worked. So where do you experience these? Most of these, they're in highway road cuts, bridge foundations. Sometimes you experience them in quarries and mines. I've been in dams and tunnels, and I've even used rock slope stability to build infrastructure underneath existing buildings. If anybody remembers Rocky going up to the Philadelphia Museum of Art, we used rock slope stability tools to actually blast and tunnel underneath that museum. Quite interesting. So those are the areas where you generally deal with rock slope engineering. And within rock slope engineering, you do have specialties related to rockfall. And so we all know this. We all see this if you have your driver's license. You can have signs such as watch for fallen rocks. You can also have other things coming off the slope as well. But there's sometimes you see watch for fallen rocks or watch for falling rocks. And if anybody is interested, the big difference between fallen rocks and falling rocks is really legal and how it's perceived in that particular state. It's who's responsible for which of those. In this particular state, in the state of Virginia, pretty much if it falls onto the road, it's the driver's responsibility to avoid it. If they get hit by the rock that's coming down, a falling rock, then it's the state's responsibility. So they have you watch out for their hazard. So it's always interesting how some of these things are intermingle between engineering and even law. Well, in a live class, I kind of pause when I show this one. This is circa mid-80s. It's along a national forest road in California. And if anybody wants to even try to recognize that particular vehicle, if anybody remembers the old Ford Broncos, I know they're coming out with a new Ford Broncos, but this is one of the old Ford Broncos. And the rock that came down was probably about 5 feet in diameter by the reports. And it came down on a road where there's only about 2 cars a week that pass on this back dirt road. Can you imagine the luck of this gentleman? The chances of that happening. And the rock went on. You can imagine hitting a car, but it really didn't have much of an effect at all. So these things can have a hazard. They have a ton of force. And one of the things that we really need to start to understand is a lot of programs do a really good job of describing and understanding soils, but rocks do act a little bit different. To show that, this is probably one of my favorite slides. In this slide, it's based on everything from Carl Terzaghi back in the 40s, and it's really simple math, but it really brings up a point. So if you're taking a look at this upper picture and the stuff over here to the left, and you assume like a typical unit weight of soils of about 125 pounds per cubic foot, and just throwing numbers out there, a typical unconfined compressive strength of about 3,000 pounds per square foot. If you were to just take a look at this math of the strength of material and the weight that's going to be over the top of it, you start to compress and crush that material when you stack about 25 feet of material. And this is just typical. And so that's why when you can only have slopes of soil that are piled up so high, you're going to have that failure down below. Well, when you take a look at the rocks and take a look at the numbers, you look at a unit weight of a rock slope, and by the way, that's a fairly low number, 150 pounds per cubic foot, and an unconfined compressive strength of about 5,000 psi. Remember, it's psi, it's not PSF. So what is that factor? 144. So it's a really significant difference, not just the 5,000 to 3,000. But when you do this math, you actually start to come out with a number that's really, really high. And so the one big question is, why don't we have very many of these mile-high rock slopes just sitting out there? And the answer is discontinuities. So when you're looking at rocks, the discontinuities in the rock mass is what controls everything. So a discontinuity is a break in the rock. It's a weakness. And there's many different types of discontinuities. You have bedding planes, foliations, faults, joints, fractures, all these terms that people learned in basic geology courses. And the interesting thing with all of these discontinuities is they don't just commonly occur once. They occur in sets, so they repeat, so you can kind of predict where they are. And when you're looking at the characteristics of these discontinuities that become really important, their orientation. So how much are they dipping? Are they flat? Are they vertical? What is the dip, the angle of dip? Which direction is it dipping in respect to your excavation? That's probably the most important characteristic that's out there. There's other characteristics that are also important. Roughness, which leads into shear strength. Water, as we know in geotechnical engineering, is incredibly important. In rock mechanics, there's a term continuity, or how through-going. Some discontinuities are more through-going than others. Sometimes you have geological situations where you have infilling material. Infilling material can both be bad and good. So you have all these characteristics that are part of these discontinuities. The biggest one in this discussion to remember is their orientation, their dip and dip direction. So when you're looking at these discontinuities, we start to take a look at their orientations. When we look at their orientations in respect to the excavation that's happening, we can get some relationships. So the first one to look at is this planar type of failure. So a planar failure is one that is failure along a single plane. And when you look at the definitions here, we have a planar failure that's located in this picture, and we have a cartoon image that's kind of showing it. So you have to have that dip direction. You have to have that dipping, and the amount of dip has to actually be steeper than the friction angle, if you want to think of it that way. So that's a good thing to think about. And for orientation for the slope face, it's got to be plus or minus within 20 degrees of your excavation, or it gets locked in. But that's a mode of failure. That means that you have some kinematic potential for the failure coming down. These modes of failures are the things that we look for in rock slope stability. So you have a planar failure, which is a failure along one discontinuity. You have a wedge failure, and here's a picture of a wedge failure where you have one plane that by itself isn't going to fail as a planar failure because it's not within 20 degrees of the slope face. You have a second plane that is coming in here, and again, by itself, it is going to be safe, but combined together, they join a wedge, they form a wedge, and that pops out. By the way, these are the wedge failures are the most common failures in rock slope stability. These are the things that we identify, and we identify them for global failures. We identify them for local failures like Rockfalls. You have other failure mechanisms like toppling, and you can even have larger circular failures, but that's more common when you're getting into different scales like big open pit mines. So we look for these orientations that are out there, and it starts to take a look at how do you interpret these orientations of discontinuities in your geologic structure and take advantage of it. And I love this picture because what we can tell is on the right-hand side, we have planes that are dipping right straight down. And you can almost imagine being a kid on a playground, how it's going to slide off into this direction. And you can see that if there was a hill on this side and it was really tall, that it would slide down and fall down this area. But on the other side, that same discontinuity is dipping back into the mountain. So that's locked in. It's locked in by the rest of the mountain. So there's not failures on the left-hand side. So this would be discontinuities oriented favorably, and these would be discontinuities that are unfavorably oriented. And as soon as you can start to identify that, then you can really start to do a good job with rock slope stability. So here's a project that I worked on quite a few years ago. It's called the Smart Road over in Blacksburg, Virginia. What we have is we have one discontinuity, and I'm going to trace it. It goes from the upper right down the lower left, and it's really, really clear in here. And if we take that same principle, it's the same thing we talked about before. By itself, it's going to be locked in. There's no failure that's going to happen along there because it's going right into the mountain. You can take a look at this other plane that goes from the upper left down to the lower right, and it's pretty apparent. And by itself, it's going to be locked in. It's not going to dip out into a planar failure. But I hope everybody can see that the two of them together form this wedge that starts to pop out and come out of the slope. So what we use stereo nets to be able to identify these types of failures. We take orientations of one set, do it with another, and put it into a relationship. It's called the Markland's failure criteria, if anybody wants to research that. And it helps us identify modes of failure, whether it be plane, topple, wedge failures. And we use those types of mechanisms. So when you're talking about engineering and we get the modes of failure, that's one of the more difficult things to do, is that mode of failure. After you get the mode of failure, you can then start to model, and you start to look at, well, what can we do to try to handle and mitigate some of these measures? And some of the things that are commonly done in rock slope stability, and this is really taking a look more at locally dealing with things. The first thing that is apparent is in some of these locations is you could blast the whole thing out, but in a lot of times you really can't because you have too many constrictions. This is a wonderful picture because it identifies different modes of addressing rock slope issues, whether they be just rock bolts themselves. And rock bolts can be dowels, they can be anchors, and the difference between dowels and anchors are ones that are post-tension versus ones that are fully grouted and passive, and they perform similar in some ways and different in others. You can have tieback areas. You can apply shotcrete, and I'll show you some shotcrete areas here fairly soon. Horizontal drains are things that are used. All of these things that are done as mitigation measures for rock slopes. And so that's when you're starting to deal with the structure and how do you prevent those plane failures, wedge failures, and topple failures. And again, so when we're talking about rock slopes, what we've been looking at and measuring is maybe more in these stabilization measures, this diagram on the left. And so we're talking about things like rock reinforcements and these types of measures to deal with geologic structure. And this is one type of mode of failure and one type of way of protecting everything. So you can reinforce it, you can blast it off, you can remove it, and all those types of measures. But probably more common as a hazard on these rock slopes, especially ones that are along Department of Transportation roads, is that they've been there for a while. Large-scale failures are probably less prone, and you're probably going to have smaller-scale failures like rockfalls. So in that case, we're going to be looking at more protection measures. And so we're going to talk a little bit about rockfalls and the different measures that you can use. And so here we're going to be talking about ditches and berms and meshes and fences and those types of environments. So when you're looking at the two different types of failures, we're looking at global failures like we talked about before. And this is through all the stereo net and kinematics and factors of safety. But then when you come over here onto the left-hand side and you start to deal with the smaller scale failures, the rockfall concerns, all of these rocks that are, this is the state of Washington, that have fallen, and we know that they've been pushed into the ditch. And there's not much of a ditch for these to fall into. Or if you're looking at this high wall area that has really been overblasted and you know these things are going to fall off, what about the hazard that presents down below? So we're going to be looking at a lot of those types of issues. The study of rockfall has been kind of interesting. It started in the 1960s with some wonderful work in Washington State. In the 80s, they came up with some more tools. One of them was the Colorado Rockfall Simulation Program, if anybody's familiar with that. This is actually freeware that you can use if anybody likes to, I started using this when it was in the DOS format. It's an interesting program. The best part about it is it's relatively free. And what it does is you put in the geometries and you put in some assumptions and you start to look at the trajectories of the rocks as they fall down. And when you start to look at the trajectories, you can calculate energies and bounce heights and things that you can do to mitigate different types of measures. And it helps you figure out what kind of mitigation measures, what happens if you put a berm at the bottom? What happens if you put a fence somewhere? It helps you with that. So some of the reasons why we want to address it is because these are hazards. And every once in a while, the thing about studying rockfall and rock slope stability is some of the pictures are just amazing. So this is a place called Athens, Ohio. University of Ohio is in this town. It used to be a heavy mining town. And all of these houses that you see on the right are built on old mining benches. And this was an old high wall. And after undercutting of a sandstone layer for some time, a large block came across. Actually, the story with this one is the gentleman was in his house. He was in the back part of this house, and he heard a big crash and a little bit of a rumble and a thunder while he was watching Jeopardy. And he came out and he saw his car was crashed. So it's actually probably a good thing that car was there so it didn't go even more into his house. But these things do present a hazard. So looking at some of the research back in the 60s with Arthur Ritchie, he did some wonderful things. One of the things that he did is he started looking at what happens when rocks start to fall down a slope. And when you start to look at it, the ideal part of a slope is to have, for rockfall, is to have a slope that is pretty much vertical. The reason why it's vertical is if a rock were to fall from anywhere on that slope and it would come down, all of its energy would be vertical. And so it would just plop and just stay right there. And the one thing that Arthur Ritchie always cautioned on is this is ideal for rockfall, but you have to have that geologic structure so that it can support this kind of vertical nature. So you have to have the discontinuities oriented so you could actually construct that. Most places don't have that and you have to lay it back. When you start to lay it back at another common angle, so this is a 1/2 to 1 or around 60 degrees, you actually start to have rolling and bouncing of the rocks coming down. You start to have some outward trajectory. And so you have to do some interesting things with your catchment area at the bottom to be able to absorb a lot of that lateral capability. As the angle starts to decrease, you start to get a little bit more rolling and you actually have more horizontal trajectory. And it does get to a point where when you get down to an angle like a 2 to 1 or around 30 degrees in that kind of ballpark, it does tend to cease a little bit. So you only have a range of generally between around 35 degrees and vertical where the rockfall is really a big hazard. So you start to take a look at the trajectories of rockfalls as they come down and be able to predict these things. So as the rock starts to come down, you have this idealized thing. Well, let's see here. I have this slope and it is coming down. And so I'm going to expect to have rocks falling out into this particular type of area. When you start to take a look at some of these models, one of the things that you have to be very careful about is if there's any launching features. And here you actually have a rim of rock that is sticking out. So if the rock's going to be rolling down this nice feature, it has potential for bouncing out and throwing itself out quite a bit further. So sometimes the charts aren't perfect. And that's where you get into some of the computer programs to be able to model and look at some of those launching types of features. Well, when you're looking at rock slopes and you're looking at launching features, we start to look at some of the common geometries that get put into these rock slopes. And when you start to take a look at geometries, one of the most common ones that are out there, especially in mining environments, is the introduction of these benches. These benches are put in for haul roads and for everything else, and usually you have, heights of about 25, maybe 50 feet high, sometimes places that are higher. And you start to take a look at rockfall. If you look at the one that's up in here and it falls onto that bench actually does a really good job of catching a lot of the rockfall. And benches can be used if you have the right geology to put these types of things in. The one word of caution especially is if you're not in a mining environment where you have machinery out there readily, sometimes your benches do get filled up and they do degrade. And they go from an original type of arrangement where they're going to be catching a whole lot of material to after they fill up, really they're creating a hazard that's much more significant and launching the features out, much like a ski jumper as they start to come out. So these things are things that you want to watch out for. Benches are great, but the other caution is you always really want to try to maintain benches. As you look at the tools that are out there to study rockfall, there's a couple of tremendous tools that should be anybody's calendar and their book when they want to get started. The stuff over here on the far left is developed initially from Arthur Ritchie, and this is the same diagram that we had before. And then a lot of the information was kind of taken from Arthur Ritchie's investigation. And what they did is they came up with this correlation between the height of your slope and the angle of your slope. And it came up with this geometry. And if anybody can take a look at these pictures, this trapezoidal shape of the width and the depth that you have to catch the rocks. So if you had a 1/2 slope that was 60 foot tall, your width would have to be 20 feet and 20 feet wide and 7 foot deep. These are really useful tools that are out there. And this was developed, back in the 80s. The one problem that they ran into is nobody made these trapezoidal catchment areas. And so around 2000, 2001, Larry Pearson with the Oregon DOT did some more research. And they actually did this with the Colorado Rockfall simulation as well. And they came up with a single angled slope for the catchment area, which is actually what's constructed out there. And so you can do the same thing with these kind of areas. You can say, well, this is for a 1-to-1 slope of a slope that's 80 foot tall. Your catchment area is 20 feet high. You can take a look at where the rock will fall, where it will get to, and where you have to do anything to contain it. This is a wonderful tool, and by the way, the Rockfall Catchment Area Design Guide, you can go and search that out on the internet. You can download the PDF for free. It's a wonderful document, and I highly advise anybody to go out there and do that. It's a really, really easy search. The one problem that you have is if you take a look at this diagram, what do you do if you only have 10 feet of catchment area? You don't have the space for any of these things to roll out, and you're going to have to do something else. And in this case, you'd be running computer models like the Colorado Rockfall Simulation Program or another program like Rockfall from RockScience and developing the tools to come up with a barrier or something else. So that gets into a case where we're talking about, how do you start to, that's a problem that we have. We just talked about a case where we don't have the catchment area. What are you going to do? And so what I want to do is I want to go through a couple of tools that are very, very common in rock slope stability and rockfall mitigations and kind of explain some of those to you and show you some advantages and disadvantages of them. The first thing I want to do is talk about on-slope treatments. So on-slope treatments include scaling, different ways of using mesh and ways of using shotcrete and the good and bad with that. We'll talk briefly about some barriers, and then we'll also look at some base of the slope treatments. But I want to spend some time on these on-slope treatments because these are the most common and cost-effective ways of dealing with them if you can do it. So we're going to be talking about scaling. If anybody hasn't seen scaling, it's a lot of fun to watch the scalers up there. They go up there with pry bars, and I'll show you some cases of it, and they remove all the hazardous rocks. And we want to think about this conversation of that's the starting point. And then we move to the next one, which is drape mesh, which is this next one over here. And that's the next one. And it's got certain things that has good and bad with that. And then we move over to the next bigger boy, which is a pin mesh, and then finally to a shotcrete surface protection and some of the advantages and disadvantages of that. So I love this video. Let's go ahead and play it. And it just shows scaling. So hopefully everybody was able to see how little effort the gentleman there doing a lot of that work is. His name is Fred. He wasn't doing much effort into there. One of the things that he was doing was just putting a scaling bar in and prying it off. And you saw some of the large blocks. If those were sitting, some of those on the ground, you would be able to move them. But since he was able to move them so quickly, see, this might be a bigger block. I think it's the same one. Yep. So when you start to take a look at some of these large blocks, there's no way a man that is strong as Fred is going to be able to move this block. But let's take a look at the amount of energy that he has to have. Fred is really strong, but he only weighs about 180 pounds.
Oh, yeah.
So when you look at what Fred did and you start to look at that factor of safety and looking near equilibrium, that rock had to be right near equilibrium because it didn't take that much energy. You can see the size of his bar that he had when he was out there. So scaling is an act where you go and you test all those discontinuities that are in the rock. And if they move a little bit, then by definition, the rock's got to come down. They got to work it out. What I wanted to do is show you this little video here on the right. And what we have is airbags that we put into behind this rock to be able to push it out.
Is that just a 70? Here she goes. Come on. I took that out. Finally.
I hope you guys are having fun watching that. So all we did was push at it with about 50 tons of force with a little airbag, and we'll show some videos. Now, this video I want to show you right now, I'm going to hit a play. There's no sound with it. This is in Montana. It's in Stillwater. I hope you can see these guys. You can see the river going. We're actually up in a drone right now, and you can see these guys. And this is in a very precarious situation. So that's about 500 tons of rock. And this video is amazing because we were tasked with not getting any of that rock into that river whatsoever. And so this is just an amazing video of achieving that. And we use berms down at the bottom and also a fence down at the bottom. I think I've got a couple of other videos of this exact one. Let me show this one on the left for you. You can see the guy standing up. This is the same exact event.
Yep, it's going.
So we're talking about 50 tons of force to move 500 tons of force and move it down the hill. That means that rock was not in a very good situation. And this video is probably one of the favorite ones to watch of the same type of failure. And right here's an airbag.
Oh man. Oh my God. Check that out. Woo! That was perfect. Perfect.
Before we move on, I just want to show everybody, this is the airbag, and that's what they use to lift up cars for fire departments. And that's all is that amount of throw. So you're only talking about something that was about 3 inches wide to it expanded at 50 tons of force for maybe 18 inches to 2 feet. So when you're looking at these things, and by the way, I hope you enjoyed those videos because it's a lot of fun. And it's a lot. There's some nerves when you're out in the field and you're doing those kind of activities. So in talking about scaling, there's different ways of scaling. The hand scaling is probably the go-to in industry. It's the one that's the most controlled. There are other mechanisms that have been employed out there. Here's a form of mechanical scaling that was employed into a mine just to get rid of a lot of the loose materials. Some places use a little bit more extravagant ways. Sometimes you can dig into the rock a little bit too much when you get into mechanical scaling, and you can almost like uncover a hornet's nest and make things a little bit worse. But the go-to is the hand scaling with the guys up there. By the way, it is a relatively safe practice. They're doing top-down operation. When they're on their way down, they're scaling everything as it starts to come down. And so them being on ropes, they have the ability to move in one way or the other and away from folks. So if you start to think about it, scaling is like going to a dental hygienist. When you're talking about your teeth, you're talking about this is where you go and get clean. This is where you get all your stuff out of there. And a lot of times you go to a dental hygienist, they say you're all clean, you're good to go. And that's the first thing I would suggest for anybody that needs to address a rock slope is go and get it scaled because they can get rid of a lot of hazards. And it does make it safe even if you have to do anything else. The second step is when you're dealing with on-slope activities is looking at a drape mesh. And so a drape mesh is a mesh that is really just like a curtain that falls on the top of the slope. And it controls rockfall. It doesn't stop rockfall, but it controls it between the mesh and the slope as it starts to come down. This particular slope had a high propensity for a lot of material coming down. We used there's a wide variety of meshes out here, and here's a mesh that's combining a double twist and a cable net type of system. There's other ones that are awesome out there that are single twist types of meshes. It's supported by a bunch of anchors that are up on the top. There's wonderful documentation on how to design these things from Washington State DOT. It's relatively easy to design these types of things. You put your anchor spacing up at the top and you just drape the mesh down below. This was actually the first drape mesh that was installed in the state of Ohio. And this is the end of it where the vegetation starting to come through. And it was catching the size of the rocks and just controlling them where once a year you can come out and pick up the bottom of the mesh and clean it out. But it does have the capability of, this was quite a bit larger than the design size that was on there. So drape meshes are effective. The one thing I would say about it is it doesn't stop rockfall, but it controls it as it's coming down. So you have to have that catchment area at the bottom, and you do have to clean it out periodically, depending on how many rock slopes you have. But it's a very cost-effective measure. Here, the drape mesh is used to cover this area and have an area where you don't have any hazards. On the far right, the same thing happened. All it's doing is getting rid of the hazard. And so once a year, they have to come in and cleaning it right near a crusher plant at a quarry facility. Drape meshes can be installed in various ways. On the left-hand picture, we're showing it being installed with a crane, that mesh. We have also installed them with helicopters. But if you look at this picture on the far right, What is it doing? It's not stopping any of the rockfall. It's not stopping any of the geologic processes. What it's doing is it's removing the hazard, because any of these rocks that fall are just going to drop out, and once a year you clean it. So it gets rid of the hazard for the passerby. So what happens if you don't have that room at the bottom and everything is really squeezed? So here's a case. This is right on the North Carolina-Virginia border, and it's right behind the bank. And you can see the roadway, the parking lot coming in, and there is no space. In that particular case, what we do is we come in and we can put in these pins, and they go through the mesh, and then the plates go down and cinch it up. And what it does is it contains, or it tries to contain everything into that slope. It doesn't stop any of the weathering processes. But what it does is it significantly minimizes that maintenance and how fast that maintenance is, and it gets rid of that catchment area that you need. But you can imagine that erosion is still going to happen in this type of product, and you will have to have maintenance in the future. But it's the next step up if you don't have a catchment area. Here's along, this is along a railroad. I apologize, folks, where we were putting up a pin mesh to make sure any of the large rocks don't fall onto the rail line, and just showing some pictures. These are really effective. And this is a perfect example of where you put the pin mesh, primarily because the rocks in this area aren't as prone to weathering. This is more in central Pennsylvania, where you're in metamorphic rocks, and it's a little bit harder, and it doesn't have differential weathering. So pin meshes is the next step up. So you go scaling, and then drape mesh, then pin mesh. But what happens if you're going to have a slope that's really, really prone to weathering, differential weathering, and changes dramatically over a short period of time? And this is very common in a lot of the coal-bearing regions. So in these regions, you have durable units. These are like sandstones and limestones. You have less durable units. These are shales and coals and clay stones and those types of units. And what happens is very quickly, these things, the shales weather away and leave these large overhangs. Well, you can kind of see the same thing that's happened. We have the anchors in there for like a pin mesh. We have this mesh that you can kind of see located in here, but we're doing something else to the slope. We're going to try to deal with that by getting rid of any of the erosion, and we're doing that by applying shotcrete. So in doing that, a couple of things I want to warn everybody about is when you're going to be applying shotcrete. The biggest thing with shotcrete is hydrostatic forces. So in this particular case, we're laying these vertical drain strips. We also employed horizontal drains in here. We do have vertical and horizontal whalers for integrity of the shotcrete, as long with the anchors. And you start to look at, here's some of the horizontal drains and us shooting the shotcrete. This project is in a place called Pikeville, Kentucky. And what we did is we armored the entire thing. This is about 5 years ago. And not only did we do this little section, but the job got quite a bit bigger, and I think I've got a couple more pictures. I know we're starting to run out of time too. So when we're starting to look at the pictures, I've got 4:30. Oh, my clocks are all home. So when you start looking at these pictures, the shotcrete is covering all of these slopes. We have horizontal drains. We have these vertical drain units. And we're starting to deal with all of these erosional issues. So you're getting rid of those types of features. And this particular area was around 2,000 lineal feet long. The slopes ranged from about 40 foot tall here to the top of the peaks at about 45 feet. And this is all a shotcrete armoring system in downtown Pikeville, Kentucky. I know a lot of you aren't from Pikeville, Kentucky, or in that particular region, but this is the home of the McCoys. If anybody's heard of the Hatfield McCoys, the famous McCoy Cemetery is right on top of this hill. And this particular road is the major thoroughfare that goes to the hospital, which is on the right of this picture. And the interesting thing about this mitigation measure is all about protection of differential weathering, so you don't have that rockfall. That's the only reason why it's there. The particular, you've got some particulars about this project, but the highlights in this is mitigation on these kind of measures. Sometimes they are more cost effective than other measures. In this particular case, for them to lay the slope back like they normally would in this type of area, because you're in the middle of a downtown, you can kind of see you're in a mountainous area. The cost of construction of doing that was estimated between $12 and $15 million, and to go from one point all the way over to the other, this mitigation was of around $4.5 to $5 million, and so you can be cost effective in these kind of things. So SHOTCRETE, and what you're looking at is a big monolith of gray. And the other thing I want to caution everybody is you don't have to do a monolith of gray. I wanted to show everybody a picture of a site. This is near Albany, New York. This is along a railway. So this is a passenger rail, and they were concerned, it's right next to a station, which is over to the right, that people would be passing by a monolith of gray. And I believe I've got a picture of it close. And this is right after construction, where the slope was sculpted and stained, and the appearance, I feel, is pretty good. And by the way, it's all vegetated now. You do have some staining of water that's coming down from the top that's really making that look like a rock type of feature. So when you're looking at on-slope treatments, you first look at this type of progression, where you want to start with your scaling, and you have safety scaling and regular scaling. That just depends upon the activity that's going on there. Scaling is maintenance. It does, your slopes do weather just like your teeth do, and you constantly have to go back and get your teeth cleaned. So it is something that has to be done periodically for rock slopes, and it's very, very cost effective, but you do have to repeat it. When you want to go to the next step up, you can go up to the drape mesh. So there is maintenance with this. We have to be clear about that. The rocks are going to fall. They are going to fall down to the bottom. It is a cost-effective measure because it's really just anchors at the top and the cost of the material and the installation of it. You do have to start to decide about which type of material, because different materials have different costs and different capabilities. You can also combine it with other things like a hybrid barrier. So this is step one. Step two, when you go to a pin mesh, you start to minimize the maintenance, but I just want to be honest, there is potential maintenance with pin meshes, especially in rocks. And in soils, you can mitigate against that a little bit more by getting vegetation to go through this stuff. It's a little bit more cost effective because it's, well, if you kind of think of it from the drape mesh, the only thing that you're adding is in these mid-slope anchors. So there is a little bit more cost to it. You do have selection of different types of meshes, and this is excellent in some geologies and not for others. And so that's step one, step two, step three, and then the big boy over at step four is the shotcrete surface protection or an arming protection. The big point on there is if you're an entity that doesn't want any maintenance whatsoever, because you're just covering and you're encasing everything. It does have the highest cost. You can start to choose with your shotcrete, whether it's fiber reinforced or the reinforcement that I showed you with the mesh and the whalers. And in some regards, it is geology dependent. So these are some of the things that you can do, for on-slope remediation options. Kind of quickly going over a couple of the other ones, there are things that you can do at the base of the slope or in some other locations. Like you can take a look at your catchment area as a way of mitigating against rockfall. You can use BERMS. BERMS are used quite a bit in mining and in quarry operations. You can use rigid barriers, and you can use flexible barriers, and there's many, many choices of those types of barriers out there in the industry. So when you're looking at the catchment areas, one of the things that we want to do is we want to try to maximize that catchment area. And in this, we start to use those tools that I was showing you earlier from Oregon DOT in Washington State with those graphs, being able to size those things. So you have the tools to be able to do it. And you start to look at doing other things if you don't have the catchment area that's out there. BERMs are very, very effective. They have high capability of absorbing capacity. But sometimes the only problem is, if it's just a pile up of material, it has a wide base that is needed to be able to catch it. So it's not very efficient, especially next to a road. It's used in quarries and mines a lot because you have readily amount of material that you can move and put into place. And that's why you see this as a delineation in many mines and quarries. BERMs are very, very effective. You can get into taking the next step, which is to take the BERM idea and kind of squeeze it. And we have been using, these are called geosynthetically confined soils, or GCS walls. These are kind of like the BERM, but we've kind of put some walls onto it on the side to be able to catch rock falls. This is in the state of New York, where there is no rockfall coming down. There's a road just about 15 feet to our left that we needed to be able to catch rocks that were about 15 to 20 feet in diameter. And so sometimes these are the measures that you need to do to be able to absorb those kind of forces, is have a rigid type of barrier that goes in there. These things can, I don't think we've ever been able to fail one of these with a rock fall. They can absorb a lot of energy. Sometimes, they have a little deformation and they're easy to fix, but these are that next step up. And the other things that you can do on the base of the slope, or even the middle of the slope, is there's a litany of manufacturers that have designed all sorts of flexible barriers. And the difference between this barrier and the last barrier is these have energy absorbing capabilities, and as the rock comes down and impacts the barrier, it's going to bow and it's going to flex and it's going to contain it. The costs of something like this is considerably less than some of the rigid barriers. But they also have limited capabilities. And so all it depends upon is running that rockfall analysis, understanding what kind of energies you're going to have in bounce heights, and picking the appropriate type of barrier that you would need. So these are flexible barriers. These are rockfall barriers themselves. And you may have also heard the term of a hybrid or attenuator barrier if you've looked at this field. And all that is it's a barrier that you put up at the top of the slope. It's the same barrier that we were just putting in before, but instead of tying it down to the bottom, you have a tail length that goes down the bottom. So it's like a combination of a rockfall flexible barrier and a drape mesh. So as a rock comes down, it impacts the mesh and it slowly works its way down the bottom for catching. When you start doing rockfall modeling, sometimes it's more efficient not to put your barrier down at the bottom, but to put it, 40 feet, 50 feet up in the air, because that's where your bounce heights are going to be the lowest. So you take a look at all of those types of barriers. So when you're taking a look at rockfall and rock slope stability, a lot of the things that we have gone over in just this bit of time is some of these mitigation measures. And so we've talked about scaling. We've talked about drape mesh. We've talked about pin mesh. We talked about SHOTCRETE application. We talked about catchment areas, BERMs, hybrid attenuators and barriers. And, these are the measures that are very, very commonly used in our field. And at this time, if anybody happens to have any questions, I'd be more than happy to answer them.
Thank you very much, Dr. Woodard, for the very exciting presentation. It was very informative. I love the videos.
Oh, those videos are awesome, aren't they?
Yeah, they are. Well, now we open it for Q&A. Those of you who are listening, and if you have any questions, just feel free to put them in the chat window.
All right, so we do have a question from online. It is the cables that were connected to the airbag. In one of your previous slides there, people were curious what that cable was, what it was made out of, I guess, for when you were using it.
To blow up the airbags, you need air. So really all it is a line, and you can even use a tank. You don't need a whole lot of pressure to blow up those tanks, but usually we have an air line from a compressor, and then usually a rope that's tied off to the airbag so we don't lose everything. But the cable that they saw was an air line.
Okay, awesome. Other question here. So could you be more specific about the most expensive option that you gave us there, the SHOTCRETE option? People are thinking about the kinds of reinforcement and steel rods, steel mesh, fibers, other kinds of reinforcement. What is it that you usually see in the field? What is it that you usually recommend?
So one of the things that's really interesting about using shotcrete on rock slopes is you really need to look at the forces. If you look at something like a soil nail wall, if anybody's familiar with FHWA, there's like circular number 7. If anybody really wants to get into the soil nail wall, and in there they're taking up on a lot of forces from that landslide that's coming into the wall. In rock slope, it's a little bit simpler, because if you put those rock anchors into the slope and get rid of the potential for a plane or a topple failure, then your forces become much less, and it becomes a surface armoring type of situation. And so what you want to do is you want to create an armoring system that is not going to fail. But the forces that are acting on there are, really, you just go through and think of all the forces. So you got hydrostatic forces, you got the weight of the shotcrete. You've kind of removed any of the forces into the ground. So you just really want to bridge any of those types of things. What I have actually moved to is the use of, I started out with a mesh. We use these high tensile strength meshes like a double twist mesh from McAfee, or even a Deltex 2 millimeter from GeoBrug. You can then put number 4 bar as rebar. And so when I'm dealing with a high degree of water, and when I know that there's going to be a lot of forces, you can put those things into there. The next step is, if you're not going to have as much water, you can start to remove that mesh and use fiber reinforced shotcrete or gunite. And then in certain circumstances, especially if it's even drier than that, then you can start to think about pulling away, some of the rebar as well. So it is a process to go through and a thought process. But you definitely want to be able to have some reinforcement in there, at least fiber reinforced in the shotcrete.
Excellent, excellent. So the next question we have is, can this work be completed in the winter months?
Really, the only thing that stops in the winter months, we actually did quite a bit of work. We installed drape meshes right next to Hudson Bay. So that's minus 45 degrees. That was pretty cold. Grouting, you can do grouting. You can heat up the water and you get the grout into the ground. As soon as it gets into the ground, then it seems to be pretty good. You do have some issues with shotcrete in the colder time periods. There are ways of mitigating it with blankets and stuff like that. But the shooting of shotcrete is the only thing that has a little bit of an issue if you start to get really cold. But you can do it any time of the year.
Awesome. And does geostabilization only fix rockfall projects? And if not, what other services do you provide?
So GeoStabilization International, we fix any forms of geohazards, anywhere from landslides to ground improvement, to rock slopes, temporary excavations, jet grouting. Any type of geohazard that's out there is what we mitigate. My particular specialty is in rockfall and rock slope stability.
All right. And on that note, when performing maintenance on pinned mesh systems, do you have to remove the mesh altogether, or is there an easier way to remove the rocks and debris?
You either cut it or you unseam it, only for a small portion, and then you put it back and seam it back up. There's different ways of seaming it, whether it's being use of a hog ring, or you use some seaming rope to tie it back together. But you usually cut the areas that that are hazardous, and hopefully you can put it back. If not, you just replace that little piece.
All right, and so there are a couple of questions here. I'm gonna kind of pile on this next question. So
Awesome.
the question is, how thick was that barrier? Was that concrete barrier or rigid barrier in your presentation?
Okay.
And my pile on is, you know, how thick can rigid barriers get, and then that you've actually seen in the field that have been designed?
So that particular barrier, it's for design. We use a ratio for the width. It's got to be half the height. So that was a 10-foot barrier tall, and so we had it as a minimum of 5 foot in width. You do have to have some width to be able to form that. That is nothing but, if you want to think of it, it's packed up and layered crushed 57 stone that's in the system. Very similar to a MSE wall, but instead of having 3-foot lifts, it's more than 8-foot lifts. If anybody wants to have any more information about GCS walls, it's a really interesting technology. And when I build a retaining wall in my backyard, it's what I use. Feel free to reach out to me or anybody at GSI. We'd be happy to talk about it. It's a wonderful technology. It's really simple.
For example, on that 10-foot tall, 5-foot wide wall, what is the depth on that?
So it's 10 foot tall. If you're looking at it in profile, it's 5 foot wide, and then it's infinite length.
I gotcha. Okay.
And you can't really do much anything. When you're compacting the material, you're using a plate compactor, so you have to have it at least a little bit wider than a plate compactor. So getting it down to a certain size does have its limitations.
Awesome. Well, thank you for answering all of our questions. I think that is all of the questions that we have online.
That is awesome. I appreciate everybody's time. I should go to that one in case anybody wants to. Here's my contact information. Feel free to reach out to me if anybody has any questions. And I appreciate everybody listening in.
All right. Well, thank you so much for such an interesting presentation. We really appreciate you taking the time to talk to our professional community today. And we have a password for today's survey. That password is Rockfall. And I will go ahead and put that up on the screen here for people to see. All right. Password for today's survey is Rockfall. Once again, thank you so much for joining us today, and have a wonderful weekend.